right, so let's start with 15 here, where we've got a ship on a stormy sea, crew members standing on a bathroom scale. Ooh, what do scales measure? No, not weight. Normal force. Yeah, well, your doctor is not as bright as you think, then. During the storm, the crew member observes a maximum reading of this and a minimum reading of this. And find the max accelerations and up and down. Alright, so this is one of the ones that we needed a force diagram for. Alright, so we actually need 3 force diagrams for this. And draw the scale, and our guy standing on the scale, or our crew member. So remember if they said male or female. Alright. Is the weight of the person going to change during this up and down motion? No, because that's their mass interacting with the mass of the Earth. Right? That's fixed. So we can draw that every time and draw it exactly the same. But in this one, let's say that they're accelerating upwards. In this one, let's say they're accelerating downwards. And in the middle one, we'll have an acceleration of 0. Okay, because we have those 3 distinct situations. Okay? So remember, the direction of the acceleration also can tell me the direction, or tells me the direction of the net force. Right? And that's kind of why I did acceleration before I do the normal force. Because I know the normal force changes. So when the acceleration is 0, that means the net force has to be 0. So my weight and my normal force, I should draw equal in size, because I think they're going to cancel out. Right? And that's why what your doctor doesn't realize there's other situations besides that. So they've taken a shortcut, which isn't a great shortcut. When the acceleration's down, the net force needs to be down, so I'm going to have less normal force than I have gravitational force. So my total force is downwards. And then when my acceleration's up, my net force needs to be up, so I'm going to have more normal force than gravitational force. So my net force, my total force is upwards. Questions on the force diagram there? All right. Let's move to the how then. And for the how, I really only need, I go to my equation sheet, but I really only need 2 equations from there. One is I need to know how the weight relates to the gravitational force, or the mass relates to the gravitational force, which is back from, I think, unit 3 or something. And then I also need what's known as Newton's second law, which says the net force equals the inertia times the acceleration, since my object is accelerating. So I'm going to put both of those so that I get that point on my rubric. Alright, and then what order do they want me to do it in? They wanted upwards and then downwards. Okay, so we'll do the upwards first, which, remember, in our diagrams is the left-handmost one. Okay. Up. So I start with Newton's second law. I have 2 forces. I have which direction should we call positive? Up. Just by convention, we'll call up positive. Okay. So I have a positive force normal minus a force gravitational equals m times a positive a. Right? So, force normal minus mg, substituting in, equals ma. Oh, I know force normal. Oh, and I know mg.
Is it 0?
Nope, this is, remember, it's accelerating upwards. Otherwise, I would have put it in 0. I know mg, that's 750. I know that force normal in this case is 910. So 910 newtons minus 750 newtons equals the inertia times the acceleration. Oh, I don't know that inertia yet. So maybe I should have done this one first, 0. Done it the exact same way. I had force normal minus force of gravity equals m times 0, right? I knew my scale reading then was 750 newtons. That's how I knew my mg was 750. And that's going to equal mg. Little substitution on the fly. So 750 newtons over 9.81 newtons per kilogram will equal m. Right? So probably just to be better precise, I should have done that first and used that over here. Use my 750, my mass. I don't feel like figuring it out right now. Times 9.81 newtons per kilogram equals 750 newtons. Okay. Oops. All right, and so the only variable is a, and I solve for a. Ready to go do the down one? Or do you see how to do the down one? Yeah, the a just becomes negative. Do you want me to write up how to do the last part? Yes? Okay.
I have a quick question. Sure. So, could you just go up for just a second? On the right-hand equation,
The red one?
yeah, you did normal force minus how'd you get 750? Like,
I read in my problem where it told me in calm waters, when there's no acceleration, the scale reads 750.
so that is just the net force.
No. See, net force is, I'm glad you brought this up. See the sigma F, that stands for net force. Subscript N, that N stands for normal. And that's what the scale reads. So if they tell me when there's no acceleration, the scale reads 750 newtons, I know the scale reads, the normal force is 750 newtons. Yeah. Remember, that's the doctor makes a mistake. Instant. All right, so down. Start the same way. Positive force normal minus force the weight equals m times negative a. My force normal in this case is 565 newtons. Minus, well, I know the weight now, so I'm just going to take that shortcut. times negative A. Rearrange and solve for A, which would be in meters per second squared. Questions? All right, so 14, we've got a sprinter that accelerates horizontally and has a magnitude of this. How much force sprinter exerts on the starting block this acceleration. And this is another force diagram one. So 14 and of course the sprinter is going to have some weight, which will produce a normal force, and then there'll be a force on them causing an acceleration. That would be the watt for it. Good, ready to go on to the how, or are there questions? So, just like the last one, we'll use Newton's second law. And they tell us the acceleration and the mass. And so really, and they ask us what the force is. The only force is F. They tell us the mass 57 and 15. 57 kilograms and 15 meters per second squared. And I'm done. And that will be in newtons. That's all there is to it. So we're going on with number 5. And landing with this speed and traveling due south, the jet comes to rest. Oh, what does it mean to come to rest? How fast are you moving? 0. You know, it's one of those understandings of the English language that helps. Find both the magnitude and direction of its acceleration. All right. So, this is number 5. The jet ends with 0 speed. Then I also would probably include something like to slow down the acceleration and velocity must be in opposite directions, right? The other kind of understanding. That means that's what slowing down means, or causes slowing down. I might put something along the lines of the further distance, the less acceleration needed to stop. Something to show that I understand that acceleration and distance are related to each other. All right. Ready to go on to the how? So, I'm going to look at my equation sheet again, and I notice I have this handy dandy relationship that relates velocities and acceleration and distance. So, I'm going to use that one. That's pretty straightforward. I mean, all my other ones have time in them, and I don't know anything about time. I could find time and then use the second equation, but V final squared equals V initial squared plus 2A delta D. And I tend to put the vector signs on those, even though they're not really vectors. But so my V final, I know that that's 0. My V initial, 84.9 for me. Abby, it's going to be a different number for you. Oh, sorry. Sorry, Abby. Plus 2. I said my acceleration and my velocity have to be in opposite directions. So I'm going to take my acceleration as negative. So that would be A, and I'm going to put a negative in front of it. And then my displacement is going to be 935 meters. So I put in 935 meters. And nicely, I can solve for A. It's the only variable in that math equation. And I'm done. People will forget the squared. Like I didn't put a squared on my 0 here because what's 0 squared? 0, but some people would be confused by that. So there you go. There you go.